Okay, so in this lecture, our main focus will be exploring the properties of ideals, and I'll try to introduce the notion of radicals in this lecture itself. And if not possible, then I'll do it in the next lecture, but I'll try to do it in this lecture, in this very lecture itself. Okay, so let's start with ideals. Now, specifically, ideals are a special type of subrings. Okay. These are special subrings, and the main motivation behind the notion of ideals is the construction of a quotient ring. Okay. Now, if you recall that suppose G is a group, so suppose G is a group, and we are talking about a quotient group of G, let's say with some subgroup H. Then if you recall, then this is defined if and only if H is normal. Okay, H is normal. Or specifically, you can also talk about it in this way, that H is the kernel of some homomorphism, and indeed it's in fact normal. So if I try to analogously extend this to the concept of rings, like rings are basically groups with an additional multiplicative structure, right? So suppose I start with a ring, let R be a ring. This is the, I'm not going to get into much greater details, but I'll just do it from the surface level. So if I talk about a ring R, then we know that this is an additive abelian group. So if I talk about any additive subgroup of R, let's say let I be an additive subgroup of R, subring of R, sorry. Yeah, in this way I can talk about a subgroup of R only. I'm talking about a subgroup of R, an additive subgroup of R. But the thing is that since R is abelian, so if I talk about any arbitrary subgroup, it's indeed normal. So I can I have a well defined notion of a quotient group. Now if I choose I to be a subring, and that is the exact symbol which I have used. So if I consider I to be a subring, then indeed it needs to be an additive abelian subgroup of R. That's quite precise. So in that way, if I talk about a quotient ring, which has exactly analogous structure or exactly analogous formation, where we take the fibers and define operations in the pre-image of the fibers, sorry, in terms of the fibers and so on and so forth, the construction is basically the same. You can also think about it being constructed using the equivalence relations, like which we have done in the groups. The construction is merely exactly the same. The thing is that for this structure to be a ring, we need to have two operations. One is your simple additive operation, which is exactly same as we did in the groups. So it will come out to be simply A plus B plus I. But we need an additional multiplicative structure for this to be a well defined ring, right? For that, we define the multiplicative structure as we would do in groups. So I'll just multiply AB and I'll consider the representative as AB. That's exactly what I'm trying to do. But the problem is that for this multiplicative operation to be well defined, if you try and structure it out, that how can you show that a multiplicative structure, this multiplicative operation is well defined? You just need to show that even if you choose different representatives of the same coset, the result is still the same. Okay, that's exactly how you check whether the multiplicative operation in this case is well defined or not. But for it to be well defined, if you carefully go through the process, you can justify it on your own. You will see that you require a closure in I with respect to left multiplication and right multiplication by elements of R. What I mean to say is that if I choose any element A from I, then I need to have RA to be in I and AS to be in I for all R in capital R and S in capital R. That is, I need closure in terms of left multiplication by elements in R and right multiplication by elements in R. And hence this gives you a special type of a subring, because I is indeed a subring. We started with a subring. These subrings are specifically what we call ideals. So ideals are basically subrings which are closed under left and right multiplication by elements of R. But if I certainly try to weaken this statement a bit, I can also talk about what we call left ideals and what we call right ideals. So left ideals are the subrings which are closed only under left multiplication by elements of R. That is, if only this happens, then we call I to be a left ideal. If only this happens, then I call it to be a right ideal. And if both simultaneously happen, we call it to be simply an ideal or a two-sided ideal. Moreover, if I talk about a commutative ring, then obviously talking about left and right ideals are equivalent, and all we get are simply ideals, right? That these things are very evident. Moreover, whenever we talk about quotient series, we can also obviously talk about the natural projection map, which also is exactly analogous to what we did in groups. We just consider an element and map it down to its equivalence class, right? So if I start with a ring R and I try to define the natural projection map, what I simply do is that I take an element A and I map it to A plus I. This gives you the natural projection map. Okay. Then the first isomorphism theorem, the second isomorphism theorem, the third isomorphism theorem, and in fact the lattice isomorphism theorem, all these statements hold analogously. There is no difference in anything. For example, if you consider a ring homomorphism, what is a ring homomorphism? So there you just need to conserve the both the operations of a ring. So on a simple note, if I consider phi from R to S, where R and S both are rings, it's a ring homomorphism if phi of A plus B is equals to phi of A plus phi of B, and phi of AB is equals to phi of A times phi of B. Okay. So if I consider any ring homomorphism from a ring R to a ring S, then I can consider the first isomorphism theorem, which simply speaks that R mod the kernel of phi is isomorphic to the image of phi. If this homomorphism is surjective, then I can further say that R mod the kernel of phi is isomorphic to S, right? And then if you have an injective homomorphism, then I can say just R is isomorphic to S. Injective plus surjective, I can say that R is also isomorphic to S. These things are very trivial to observe. Moreover, what are the only subrings in Z? The only subrings in Z are the ones of the form NZ. These are the only subrings in Z. So typically, the only ideals in Z will also be of the same form, right? And in fact, these are the only ideals and these are the only subrings typically. Clear? I guess this is very trivial statements. There is nothing too complicated to talk about. Moreover, I can talk about the sum of two ideals and the product of two ideals in this way. That suppose I choose I'll use this symbol to give you ideals. Suppose I choose I and j to be ideals of a ring, then I can define I plus j to be the sum of the elements individually in I and j. So I can talk about this like A plus B such that A is in I and B is in j. Then I can talk about the product of two ideals, but here the definition is not as intuitive as it seems to be. We define it to be the finite sums of elements of the form AB such that A comes from I and B comes from J. We don't simply define it to be the product of the elements from I and J. Okay, that is not always additively closed. Okay, so this is the exact definition we require for product of ideals to hold. And this symbol often means finite sum. When if I don't mention anything, whenever I use this symbol, you'll get to know that we are talking just about a finite sum. So I can inductively extend this concept to define what we call the power of an ideal, exponents of ideals. So this is again simply by definition the collection of finite sums of the elements of the form A1, A2 till AN, where each AI comes from I. Okay. If you just try to justify these a bit, you will observe that the ideal I plus j is the smallest ideal which contains both I and j, and this ideal ij, the product of the ideals ij, it's necessarily contained in the intersection of I and j. Okay, try and justify this out. Clear? Okay. The thing which I specifically want to talk about in this lecture is the notion of a principal ideal. Now, what is a principal ideal? So, principal ideals are analogous structures to cyclic groups, right? In case of cyclic groups, if you recall, we started with a single element and we extended the element by composing it with itself to form a group structure, which came out to be known as a cyclic group. In this case, we do the same thing, but like in this case, we can't, the way we expand an element is by taking elements from the whole ring R and considering a linear combination of those elements, or considering simply the multiples of those elements. So in this way we can extend it out. What I am trying to say is that, let's say suppose A is a subset of R. Suppose A is a subset of R, and throughout this section we necessarily assume R to be a ring with unity, that is R has a multiplicative identity. Okay, so R is a ring with unity. R is a ring with unity. How do we define what I want to say is that, suppose I choose A to be a subset of R, then I define the ideal generated by A, which is again analogous to what we did in groups, is the smallest ideal containing A. And to give a structure to this, what we typically do is that we try to construct how the elements should look like. So what I do is that I consider this structure, which is defined as the elements of the form R1A1, R1A2 till R1 Rn such that each Ri comes from capital R and each Ai comes from capital A. Similarly, we define AR to be, so I guess now it's analogous. So I started with A1 R1 and I continue it till An Rn, and then again that each Ri comes from capital R and each Ai comes from capital A. Similarly, if I talk about this structure RAR, then this is also as a natural definition. It comes like R1 A1 R1 dash, and the addition continues till say Rn An Rn dash, where each Ri comes from capital R and each Ai comes from capital A. Okay. Now if A is a singleton set, then the ideal generated by A is simply written like this: the ideal generated by the singleton, the element small a, and in this case we say this ideal to be a principal ideal generated by A. Moreover, if this set A is finite, then we say the ideal generated by A to be a finitely generated ideal. The thing which is very easy to observe, if you have basic knowledge in group theory, you can easily justify this out, that Ra is typically the ideal generated by A whenever A is a left ideal, and AR is the ideal generated by A whenever A is a right ideal. Moreover, if R is commutative, then all these structures are equivalent. Talking about RA is same as talking about AR, is same as talking about RAR, and all these equal the ideal generated by A. Okay. So by simple definition, if I talk about the principal ideal generated by A, it will simply come out to be the collection of all R multiples of A. R multiples of A means that we choose elements out from R and multiply it to A and construct the set out of that. Okay. Now the question is that why are principal ideals important? Now typically whatever concepts we try to study or try to examine in rings, they somewhere comes as a generalization for what happens in the ring of integers. Okay. For example, when we will study prime ideals, we will also see a notion that how we generalize the concept out from what happens in the ring of integers. For example, if I talk about if I talk about an element M which is inside the element which is inside the subring nz or the ideal nz, okay, then you can easily observe, then I can write M as n times an integer, but that typically means n must divide M, right? That typically means n must divide M, right? Similarly, I can also talk about like this, that if mz is contained in nz, then this typically implies that n must divide M, right? Moreover, for equality, I need to have a both sided division. That is, if I say that mz equals nz, then I must have that n divides M and M divides N. Now, these are very trivial structures. Similarly, we can sort of talk about generalized notions of this, which also immediately follow from how the principal ideals are constructed. That is, if I consider any element in the ring R and I say that B is contained in the ideal generated by A, then observe that B can be written as some R multiple of A. We are talking about ideals. We are not specifically talking about left or right ideals. We are simply talking about ideals, two-sided ideals. So I have some element in capital R such that I can write B as a multiple of A with respect to that element R. I better write it like this, AR. But that immediately means that A divides B in the ring R. That should be precisely mentioned, that A divides B in the ring R. And in a way, this also you can just relate these two out, right? Clear? Okay. Moreover, let's come to the ring of integers. You can easily observe that if say D is the GCD of N and M, then the ideal generated by N and M is simply the ideal generated by D. Therefore, if I see, in a way, I am trying to bring down finitely generated ideals to principal ideals, which I can surely do in case of the rings Z, the ring of integers, right? So whenever I talk about two integers from the ring of integers, I can simply talk about the greatest common divisor of them. Hence, whichever integers I choose, say N and M I choose from integers, I can talk about a GCD of them, say D, and then I can bring down the finitely generated ideal using N and M to the principal ideal generated by D. Moreover, if we talk about co-prime ideals, suppose D is 1, then I get the ideal generated by N and M to be simply the ideal generated by 1. But if you carefully observe that ideal generated by the multiplicative identity is the whole ring, because this will contain elements of the form R times 1, where R comes from capital R. So in a way, the capital R should be contained in the ideal generated by 1. But by definition, 1 is in R, so the ideal generated by 1 should also be in R. So we have a both sided inclusion, and hence they must be. In fact, ideal generate, we can say something more. We can say that if I talk about any ideal which contains a unit, then that ideal must be equal to R, and this is a if and only if statement. Okay, so let me just present it as a theorem that if I is an ideal in R, then number 1, I contains an unit, if and only if I equals R, and number 2 is that R is a commutative ring, then R is a field if and only if its only ideals are 0 and the whole field R. Okay. So how do we prove this? The proof is fairly simple, because see, if I equals to R, then it necessarily contains an unit which is the multiplicative identity itself. Conversely, if I say that U in I is a unit, then this implies there exists some V in R such that V times U is 1, right? But then this must be exactly inside I, because V comes from an element R, and since we are talking about an ideal, so it must be closed by multiplication by elements of R. But if 1 is in I, this means for all R in capital R, R times 1 is also in I, or in other way we have the both sided inclusion again, because R comes to I and then I is obviously included in R, so we have a both sided inclusion, right? So this proof is fairly simple. Next proof is also fairly simple, because for example, if I say that the suppose R is a field, let's say R is a field, then all its non-zero elements are units, right? Say R is a field, then by definition all its non-zero elements are units. If I choose any ideal which is non-zero from R, then I specifically contains at least one unit, right? Because every non-zero element in R is a unit, but if it contains a unit, it must be equal to R, right? Conversely, what I can do is that I can simply assume any element out from R which is non-zero, which is specifically non-zero, and I consider the ideal generated by U. Okay. Now, since U is a non-zero element, the ideal generated by U is surely not 0. But by our hypothesis, every ideal, the only ideals in R must be 0 or R. So this implies the ideal generated by U must be the whole of R. But that means that U is a unit. That means U is a unit. Because 1 is in R, so why does this follow? Because 1 is in R, and since the ideal generated by U is the whole of R, this specifically implies that there exists some V in R such that UV is equals to 1, which necessarily means U is a unit, right? This has an immediate corollary which is also very important, which says that if you talk about any non-zero ring homomorphism from a field to any arbitrary ring, then that homomorphism must be injective. Okay. Corollary: if phi from F to R is a ring homomorphism where F is a field and R is any ring, and R is any ring, is a non-zero ring homomorphism, R is any ring, then phi is injective. How does this follow? See, if I talk about the kernel of phi, then kernel of phi is necessarily an ideal of F. You can easily justify this out. That's a very easy proposition, that the kernel of a ring homomorphism is an ideal. So if kernel of phi is an ideal of F, then, and F is a field, so that means that kernel of phi either can be 0 or can be F, but it cannot be it cannot be rightly or the whole of F because it's a non-zero homomorphism. So therefore it needs to be 0, but if it needs to be 0, then phi is 1 1, right? Clear? Okay. Now, as I previously discussed the fact that if I talk about finitely generated ideals in rings, in the ring of integers, then I can try and bring it down to principal ideals, but obviously I can't do it in a general note. For example, if I talk about the ideal generated by the element 2 and x in Zx, then it's not a principal ideal. It's not a principal ideal. How does this follow? See, first thing first, let us give a structure to this ideal generated by 2 of x. So by definition, the ideal generated by 2 and x, it's simply the elements of the form 2 times p of x plus x times q of x, such that p and q both elements come from Zx. What is the ideals? What is the ring Zx? So it is the set of all polynomials with coefficients coming from Z, and the operations are specifically the simple, the component wise addition and the Cauchy product of multiplication. There is nothing too complicated there. Moreover, if I have this structure, then you can easily observe that then this is simply the collection of all polynomials fx from Zx, such that the constant term is even. That's that the constant term is even. You can fairly observe it in this way, that this term will have no constant term, because the constant term will get multiplied by x, while in this case the constant term is being multiplied by 2, so we transform the constant term to even, and when I add up these two polynomials, then the constant term is same as the constant term in 2 times p of x, and that hence that's even. So it's fairly easy to observe. Converse statement you can also talk about, that if you consider this set, then you can equivalently say that it's exactly the same set we talked about previously. Clear? So now, if we talk about if you're talking about polynomials with the constant term being even, collection of all those polynomials with constant term being even, then clearly this forms a proper ideal of Zx, right? Because every polynomial in Zx need not have a constant term, even constant term. Okay. So suppose this is a principal ideal. Suppose this is generated by some ideal Ax. Okay. Now 2 belongs to the ideal generated by 2x. So this means 2 belongs to the ideal generated by Ax. But this implies that there exists some polynomial, say qx, such that I can multiply Ax with, say, bx. Let us do it with bx. But now observe that Zx is an integral domain, right? Because that is, it has no zero divisors. And why is it an integral domain? It's an integral domain because Z is an integral domain. Now you can justify this out that if you choose polynomials out from an integral domain, out from a polynomial ring which is an integral domain, then if you consider the product of two polynomials, then the degree of the product is same as the degree of the addition of the degrees of each polynomial. Okay, that simply follows from the fact because the leading coefficient needs to be 0 by definition of any polynomial. If you talk about polynomials from non-integral domains, then there is something else, because suppose I talk about polynomials from Z4x and I consider the polynomials at 2x square plus 1 and let's say 4x square plus 2. Then if I multiply this out, what do I get? I get 8x to the power 4 plus 4x square plus 4x square plus 2. Now if you carefully observe, so I get 4x square plus 2. So if you carefully observe, this becomes 0 because now the operation in this case is multiplication modulo 4, because we are talking about coefficients from Z4. So this will become 0, this will also become 0, you are only left with 2, right? So the degree is not valid, the statement for the degree is not valid, but it will trivially hold in case of integral domains. So in this case I can write that this implies that degree of A plus degree of B needs to be 0. But we are talking about non-negative elements, so this simply implies that both must be 0. The degree of A must be 0 as same as degree of B, but then that typically means that A and B come from integers, they are simply integers. But now I have a factorization of the prime 2. So this typically means that either the polynomial A needs to be plus minus 1 and correspondingly B needs to be plus minus 2 and vice versa. So I can just simply write it like this, that A and B can be respectively considering the values plus minus 1 and plus minus 2. Okay. Now see, A cannot be the ideal generated by plus 1 or minus 1. See, AX, if AX is equals to plus minus 1, then that implies the ideal generated by AX is the ideal generated by, let's say, 1. 1 or minus 1 will trivially be the same, but if you carefully observe that this is exactly equal to the ideal generated by 2x. Now this is a proper ideal of Zx, but if it was to be equaling the ideal generated by 1, ideal generated by 1 will be the whole of Zx. So if it is the whole of Zx, then it cannot necessarily hold, right, because it is a proper ideal. If it equals the ideal generated by 1, it must be the whole of it, whole of Zx. So that doesn't necessarily hold at all. Clear? How can I talk about a converse of this statement? Oh sorry, how do I talk about the now the second operation? So I need to assume that the polynomial Ax needs to be either plus 2 or minus 2, right? So therefore the ideal generated by Ax must be the ideal generated by 2 or the ideal generated by minus 2, right? But now observe that this is exactly equal to the ideal generated by 2 and x, and x is necessarily in this ideal, but that means that x must be equal to 2 times a polynomial say qx, and this is impossible, right? This is impossible because the coefficient on the left hand side of x is 1 and on the coefficient on the right hand side of x must be an even number. That's not possible, right? So therefore in both cases we have a contradiction, and these are the only two cases. So therefore this cannot be a principal ideal. The ideal generated by 2 or 2 and x cannot be a principal ideal. Okay. Now let's introduce the ideal which I want to discuss in this lecture itself, which is the concept of a maximal ideal. Okay, a maximal ideal. A maximal ideal. So a maximal ideal is a proper ideal which is not contained in any other proper ideal. An ideal M in R, strictly contained in R, is said to be maximal, if the only proper ideal in R containing M is M itself. Okay, there is no other proper ideal in between M and R. Clear? Now it is easily observable that if I talk about a field then the only ideals are 0 and the whole field, In fact, the only proper ideal is 0. So the only proper ideal in the field which contains 0 is the 0 ideal. Hence it is the maximal ideal. Can I say that every ideal must contain a maximal ideal? That's necessarily not true. Now why is it not true? Because if I talk about any arbitrary abelian additive group, I'm just stating it out. If I talk about any additive abelian group, and I form it into the trivial ring. How do I form a trivial ring? So suppose G is an additive abelian group. I give the multiplicative structure to G is as that. So for all A, B in G, I define multiplication by just mapping it to 0. Okay. This gives you the trivial group. This is called a trivial group. So therefore any group can be constructed into a ring trivially. But in this case, when we are talking about a trivial ring, so this is not called a trivial group, I am very sorry, this is called a trivial ring. So if I talk about any trivial ring, the subrings are specifically subgroups. So if I necessarily talk about a subgroup, an additive abelian group which has no maximal subgroup, then we are done. Then that then the trivial ring induced by that very group will have no maximal ideal, right? Because it indeed has no maximal subring, because it has no maximal subgroup. One such group is the additive abelian group of rationals. The additive abelian group of rationals has no maximal subgroup. Clear? Okay. But I need to characterize its existence because we have successfully defined it out. To do that, proposition in a ring with unity, any proper ideal is contained in a maximal ideal. Okay. Now how do we do that? Now necessarily, see, in basic set theory or in the concepts of set theory, the most useful element or the most useful tool to talk about maximality in some set is the Zorn's lemma. And if you recall what a Zorn's lemma is, it says that if I talk about a non-empty set A such that A is a partially ordered set and every chain in A has an upper bound in A, and every chain in A has an upper bound in A, then A has a maximal element. So we try and frame it out in a similar way. How do we prove this out? What we do is that, so R is a ring with unity, therefore R has a non-zero element, at least that is 1, right? 1 minute guys. That is 1. Now if I choose any proper ideal is contained in a maximal ideal, so how do I successfully do that? So let S be the collection of all proper ideals of R, containing I, right? Now necessarily S is non-empty, as I should itself be contained in S, right? Moreover, we considered, and moreover S is if you observe that S is a poset with respect to the inclusion ordering. So I can consider an arbitrary chain from S. So what is necessarily a chain? So it's just like this form. So I choose ideals I1, I2 such that each is contained in the next. Okay. And what we do is that we consider, so if I talk about a chain in this form, then what should be the natural upper bound we should talk about? It's the union of these elements. So let J be the union of all the ideals A where A is contained in this chain. Okay. But then does J necessarily belong to this collection S? That's quite obvious, right? Because firstly J is an ideal and J is in fact a proper ideal of R containing I. Okay, how do we show this? Observe that firstly J will contain I by definition because J is the union of all ideals which contain I. Moreover, J is closed under multiplication by elements of R because if I choose any element from J, then that necessarily means that A is in A for some A in the chain C, and each of these ideals A is each of these are ideals. So therefore, if small a is contained in capital A, then since capital A is closed under multiplication by elements of the ring R, so this implies that RA must be in capital A, but this again means that RA is in J. Similarly, you can also talk about right multiplication. If I talk about addition, sorry, if I talk about subtractive closure, then if you choose two elements from J, then this means that A belongs to say capital A and B belongs to say capital B, such that where A and B are coming from the chain C. But if you observe that since we are talking about a chain, so either A is included in B or B is included in A. But if A is included in B, then A and B both are in capital B, and the same happens here also. A and B both are in capital A. But since A is an ideal, so A minus B is in capital A, and in this case also A minus B is in capital B. But that means that A minus B is in J, and in this case also A minus B is in J. So J is in fact an ideal. Therefore J is in fact an ideal of R containing A. Moreover, it needs to be proper because if it equals 1, then that implies 1 must be in J, but that implies 1 must be in A for some A in the chain C. The chain we are constructing out from the class S, but every element in the class S is a proper ideal. So we reached a point where we are talking about an ideal A from S which is not proper, because if one is in that ideal, then it cannot be proper. So it's a contradiction. Right. Therefore J is a proper ideal containing I in R, which necessarily means that J must be in the same collection S. Okay, J must be in the same collection S. But then C was an arbitrary chain, right? So we have got a non-empty partially ordered set where any arbitrary chain has an upper bound in the same set, and then by Zorn's lemma we can say that S has a maximal element, and exactly that maximal element is the maximal ideal we are talking about. That can be easily justified now. I hope this part is clear. Okay. The next statement is far more important to observe, which is the proposition that let R be a commutative ring with, let's say it's a commutative ring. We have already assumed it containing unity. Then M is maximal. M is maximal if and only if R mod M is a field. Okay, R mod M is a field. How do we prove this? Now proving this is fairly simple, because if you recall the isomorphism theorems, then we had said that the ideals of, so if I relate that to this case only, so if I consider any arbitrary quotient ring, then the ideals of R mod I has a 1:1 correspondence to the ideals of R containing I, right? That's quite a trivial notion, right? Therefore, if M is a maximal ideal, then the ideals containing M in R are only R and M, right? Therefore, the ideals of R mod M should be just 0 or R mod M, but that necessarily means that R mod M is a field. R mod M is a field, and all these statements are equivalent. right? Clear? So this is a very easy proof. This actually gives us very important observations. For example, if I talk about the quotient ring Z mod Nz, then we know that this is isomorphic to simply Zn, right? But this is not a field. Zn is not a field for any arbitrary integer. It's a field if n is a prime. If n is a prime, right? So therefore, Z mod Nz arbitrarily is not, sorry, Nz is arbitrarily not a maximal ideal, but it's a maximal ideal if n is a prime, or if and only if n is a prime. So I can talk about the fact that Nz is maximal. Nz is maximal if and only if n is a prime. Clear? And we will end this lecture with respect to the next example only, and in the next lecture we will be introducing the concept of prime ideals, and then we will be introducing the concept of radicals. Okay, we will very briefly discuss radicals. Our main focus will be prime ideals. This example is quite important, which says that the ideal generated by 2 and x is maximal in Zx. How do we do this? See, it suffices to prove that Zx mod the ideal generated by 2x is a field. How do we do that? Carefully observe this. So this is an arbitrary justification. You can understand the proof once we justify these statements. If I consider a map P from a polynomial ring to the ring itself, such that P sends, or let me write it simply like this, so that any polynomial fx is sent to f0. This is called an evaluation map at 0. We can also evaluate it to any arbitrary integer. We can evaluate it to, say, c. So that in that case we will talk it evaluation map at c. So this is the evaluation map at 0, and if you carefully observe, the kernel of this map are all the polynomials which have no constant term, which have 0 constant term. Now I start with such an evaluation map at 0, let's say, and I consider another homomorphism, say phi, from R to an arbitrary ring S. But so let me write P like this. But then if you observe, then I can directly map Rx to S by just composing out phi and P, right? And this will indeed be a homomorphism again, right? So we do the same thing. What we do is that we take R to be Z and we map Zx to Z mod 2Z. How do we do this? We consider a polynomial Px, we map it to P0, and we then map it to P0 mod 2. So this will be a homomorphism clearly. In fact, this homomorphism will in fact be surjective, right? What should be the kernel of this homomorphism? The kernel of this homomorphism will be the collection of all polynomials Px in Zx such that P0 is 2, P0 mod 2 is 0. So such that P0 is inside 2Z, or in fact the constant term is even. I guess now you can relate this to what I am trying to prove. In other way, if I consider this whole map to be F, then I can say that Zx mod kernel of F is isomorphic to Z mod 2Z, because this map is clearly surjective. But what is kernel of F? Kernel of F is the collection of all polynomials with even constant term, and hence the kernel of F is simply the ideal generated by 2x. So it's isomorphic to Z mod 2Z. But 2Z is a maximal ideal because 2 is a prime. So Z mod 2Z is a field, which means that this is in fact a field. But if this is a field, then the ideal generated by 2 and x is a maximal ideal. Got it? But immediately we can also prove the following, that the ideal generated by x in Zx is not maximal. And why is it so? Because see, this is the kernel of the evaluation map at 0, where P is the evaluation map at 0, right? and it's a surjective map. If you carefully observe, it's indeed a surjective map. So simply I can say that Zx mod the ideal generated by X is isomorphic to Z by the first isomorphism theorem. Z is not a field, so this is not a field, hence this is not a maximal ideal, right? And you can trivially check this out because the ideal generated by X is contained in the ideal generated by 2X, and the ideal generated by 2X is properly contained in Zx. So indeed it's simple observation that it's not a maximal ideal. In the next lecture we will introduce the notion of a prime ideal, and we will try to relate maximal ideals and prime ideals, and then we will be introducing the notion of radicals. Okay, so meet you guys in the next lecture.